Hello students, welcome back. So last class we studied what are coordination compounds and what are the different terms linked with coordination compounds, how to write the name of coordination compounds. So here there are some examples. We have to write their IUPAC names, according to what are the names according to IUPAC nomenclature, and here there are some names. Here we have to write what is its formula. Okay, so first let us start how to write the names of the compounds. Look here. So first K2HgI4. So this is the cation part, this is the anion part. So the name of this compound is potassium mercury. So first find out what is the oxidation number of this. The oxidation number of mercury is found to be, suppose this is X, potassium has +1, so 2 plus 2 into +1 plus X plus 4 into -1 equal to 0. In this X equal to +2. So we have to write this by Roman letter, and this part is negative part. That means we have to use its Latin name, and that should be end with ATE. So in this way, the name of this compound is potassium. This is name of this compound is potassium, and while writing this complex part, first I have to write what are the name of ligands. So this is tetra, iodide ion is there, so iodido, potassium tetra iodido, mercurate 2. Okay, so the name of this compound is potassium tetraiodido mercurate 2. Okay, next come to name of this compound. So NaAuCN2. This is also a complex part, and this is sodium. Sodium has +1. So first find out what is the oxidation number of Au. That is your +1, and cyanide has charge as -1. One cyanide, two cyanide, -2. In this way, you have to find out what is the oxidation number of this. So name of this compound is sodium. Name of this complex part, just give a little space between cation and anion. But whenever you write the name of complex, at that time don't give any space. That should be written just by one word. So this is sodium dicyanide. Cyanide, that can be also written cyano. So potassium dicyanide, Latin name arum, arate, and ATE. So left ends with ATE. Oxidation number is 1. In this +1. So name of this compound is sodium dicyanide arate. Next come to this one. Answer number 3. This is answer number 1. This is up 2. Now come to 3. K3Fe2O4. Here also the complex part is in negative charge. Here also the complex is in negative part, and this is the oxalate ion. This oxalate ion has charge -2. As this oxalate has charge -2. This oxalate has charge -2. So in this way, and find out what the oxidation number of this. So oxidation number of this found to be 3, because look here, potassium has +1, 3 into +1 plus X plus 3 into -2. All total this is equal to 0. In this same X plus 3 minus 6 equal to 0. X equal to +3. So the oxidation number of iron here found to be 3. So in this way, what is the name of this compound? The name of this compound compound is potassium trioxalato. This is a negative ligand, ends with O. Potassium trioxalato ferrate 3, followed by its oxidation number in parenthesis. Next, K. So 3 is over. Now come to 4. PTNH3 whole 6Cl4. In this case, this part is a positive part. As this part is positive, so no need to write the Latin name or that end with AT. That ends as usual in the form. That is your English name is its used. Its English name is used. But whenever you write the complex part, first you have to write the ligand name. If more ligands are present, then you have to use the numerical prefixes. So there are 6 number of ligands in this way hexa. So name of this compound is hexa and amine. For ammonia, amine is used. Hexaamine, platinum, hexaamine, platinum, and then find out oxidation number. Ammonia is a neutral ligand, so this is X plus 6 into 0 plus 4 into minus 1, all total that is equal to 0. In this way, X equal to plus 4. So hexaamine, platinum, 4 numerator, then give slide space, then chloride. No need to write tetrachloride. Okay. Next come to question number 5. In 5, COF2EN2ClO4. First find out what are the ligands. F, this is chlorido, and En, that is ethane diamine, or we can say ethylene diamine. Ethane 1,2-diamine or ethylene diamine. As in its name, already the numerical prefix di is used in this way. If more number of this type of ligands are present where numerical prefixes are already there, at that time we have to use bees, trees, etc. So fluorido and ethylene diamine. So in ethylene diamine and fluorido, first alphabetically first comes your ethane diamine. In this way it should be considered. So whenever you write the different number of ligands, at that time the number of ligands that are the numerical prefixes are used, that are generally not considered for alphabetical order. For example, this is ethane diamine and this is difluorido. Although difluorido, here the D is not considered, but fluorine is considered, fluoride is considered. So in fluoride and ethane diamine, what are the ligands? Give importance. What are the ligands? So even what is the name of the ligands? If the name of the ligands which comes alphabetical order, that should be written first. This is fluoride and this is ethane diamine. This present 2 times, this also present 2 times. So the coordination number of this is 2 and 2 plus 2 into 2 because this is a bidentate ligand. So in this coordination number is 6. So this is your perchlorate ion. So what is the first find out? What is its oxidation number? So its oxidation number is X plus 2 minus 1 plus 2 into 0 because this is a neutral ligand plus minus 1 equal to 0. In this X equal to plus 3. Okay, oxidation number of cobalt here plus 3. So what is the name of this compound? The name of this compound is, so first you have to write the ligand name, and within this ligand should be written first. So this is bis, then give bracket. After writing bis, if the organic ligands are present or the ligands which contain numerical prefixes, or that are generally represented in parentheses, in brackets. So bis, ethylene diamine, or ethane 1,2-diamine. Here for amine only single name is used. Okay, bis ethylene diamine continue. Cobalt and oxidation number 3 in numerical Roman numeral cobalt 3, and this is perchlorate. Perchlorate. Okay. Next come to question number 6. CO, SO4, NH3, 4, NO3. This is sulfate and this is amine. So amine comes first, but in sulfate charge is -2, nitrogen charge -1. In this ammonia is neutral. In this cobalt has charge +3. Its oxidation number is +3. So what is the name of this compound? That is tetraamine sulfato. Tetraamine sulfato cobalt 3 nitrate. Tetraamine cobalt 3 sulfate, tetraamine nitrate. So I have given a boundary here. Okay. So next CO, SO4, NH3, 4, NO3. Okay, so 6 is over. Next come to 7. CO, NH3, 6, Cl3. This is simple compound. This part is positive, this part is negative. So in this way 7 has answer. Hexaamine cobalt 3 chloride. Okay. Next come to question number 8. So lithium is there. Here instead of transition metal, another metal atom is there. That is aluminium. And what is the name of this compound? Name of this compound. This is positive part. This is negative part. So first positive part is written, then the negative part. In this way, name of this compound is lithium. So hydride ion is there and 4 numbers. Tetrahydrido. H minus hydride, from hydride, hydrido. Lithium tetrahydrido aluminate. Because this is negative part, so AT and so AT. Because for aluminium there is no Latin name. In this English name is used, and we have to write ATE. So lithium tetrahydrido aluminate 3. Oxidation number here 3. Next. CONO2 NH3 5. So these 9 and 10, these two are same, but here almost same, but here this is linked with NO2 and it linked with ONO. So these are ambidentate ligands. Okay, NO2 and ONO are ambidentate ligand. In this case, what ligand is present, we have to write the point of attachment of the ligand. This point of attachment. So CO, NO2, NH3 5, 2 plus is there. So for that, this is nitro and this is amine. So first you have to write amine. So name of this compound is pentaamine nitrito. Here this is linked through nitrogen. As this linked through nitrogen, so this coordinate through nitrogen. As it coordinates through nitrogen, we have to write nitrito N. So the point of attachment we have to write nitrito N, then cobalt and charge, it has -1 and it has 2 plus charge. In this way, cobalt has charge +3. Ammonia has charge 0. So, pentamine nitrito N cobalt 3, and this is an ion. So, we have to write ion. Similarly, for 10 number, the name is pentamine nitrito O. They are linked with oxygen. As it linked with oxygen, pentamine nitrito O cobalt 3 ion. So in this way, we have to write what are the names of IUPAC names. So these are some simple examples to write the IUPAC name of compounds. Okay. Now next comes how to write the formula of these compounds. So names are given and how to write the formulas. So to write, if the formula is given, the name is the formula given, then how to write the names, you know. Then if the names are given, how to write the formulas. So if the names are given, then to write these formulas, if the names are given, then to write these formulas, first we have to write the formula for cation, then we have to write the formula for anion. First for cation, first anion, and if whenever we write the name of ligands, whenever we write the name of ligands, at that time, so the name of the complex part, whenever we write the name of complex part, first we have to write the central metal atom, then followed by ligands. If more number of ligands are present, then these are represented by numerical letters. Okay. And next, if compound ligands, if any ligand consists of more than one atom, polyatomic ligands are present. If polyatomic ligands are present like ammonia, water, etc., then these are represented in brackets. Polyatomic ligands generally represented in brackets. Next, if different ligands are there, then all these ligands are arranged according to their alphabetical order. If different ligands are there, then these are arranged in alphabetical order. And after writing the metal name, after writing the symbol for metal and what are the formulas for the ligands and how many number of ligands, then we have to balance what is the charge present on the complex ion with this ionizable part. Because total positive charge should be equal to total negative part. In this way, we have to just multiply if necessary, then multiply by suitable number, and then we have to write what is the formula of the compound. Now let us start. Look here for some examples. Okay. So first, sodium tetrafluoridoxidochromate. Given from this name, we can given sodium tetrafluoridoxidochromate. So from this we know this is a cation part and this is anion part. This is cation part and this is anion part, and the complex is the anion part, and the complex is the anion part. Okay, this is cation part, this is anion part, the complex is anion part because it ends with AT. And what is the metal atom here? Here the metal atom is chromium. Okay, here the metal atom is chromium. So first positive part, I am writing here sodium. And then for complex part, I have given the square bracket. The complex part should be written in square brackets. This is square bracket, and given sodium tetrafluorido, oxido. So in alphabetical order, fluorine comes first. If the symbol of fluorine comes first, then that of oxygen, that is oxide. So alphabetically, fluorine comes first. So first chromium, okay, the metal atom is central metal. Sodium tetrafluorido, oxido, chromate. So Cr, then F4, then O. One oxygen, oxido, fluorido. Now what is the charge? Given 3. So if the charge of chromium here 3 and fluorine has charge. So up to this is the ligand. So it has charge is +3 and fluorine has charge how much? Fluorine has charge -1. So 4 fluorine. So 3 plus 3 plus -4 and -2. Okay, +3 +4 -2. In this complex part has charge -3 and this has a charge -3 and sodium has charge +1. Just crisscross this number, then you can find out the formula, and the formula of the compound is Na3Cr F4O. Okay, now clear? Now let us discuss other parts. Amine aqua dibromido copper 2. Amine aqua dibromido copper 2. So from this there is no negative part and there is no positive part. Only one part is there. From here the formula you know this is the complex is totally consists of one part. Then so first metal atom is copper and amine and aqua. Amine NH3, aqua H2O. Alphabetically H2O comes first in this way. Cu H2O. Then bromido is there. So first bromido comes first. Cu dibromido. So Br2. Then H2O. This is kept in parenthesis. Then NH3. Okay. Then NH3. So not total charge is balanced. Okay. So this is amine aqua dibromido copper 2 complex. Next come to question number 3. Potassium tetracyanido cuprate. So charge given to this is the positive part and this is the negative part. So in this way, name of the compound first potassium, then cuprate. So copper is there in complex part, copper, and charge is 2 tetracyanido CN whole 4. No other ligands are given. Okay, so at the total charge is here whole 4. Cyanide has -1 charge. So this copper has charge +2 plus -4. This is equal to -2. So this complex has charge -2 and this has charge 1. In this way, just crisscross this number, that is K2 Cu Cn4. Next come to question number. Next come to number 4. Diamine dichlorido platinum 2. Diamine dichlorido platinum 2. So diamine dichlorido platinum 2. So in this is also one word. So first write down platinum and amine chlorido, amine NH3, chlorido is Cl. So first write down the formula for Cl, dichlorido. So Pt, then Cl2, then NH3 whole twice. So this is platinum dichlorido diamine, and this is -1 and it has +2. In this platinum has +2. In this way, this charge is balanced. This is the single compound. Okay. Next come to potassium pentacyanido nitrosyl ferrate. So potassium given and this is as given. From that we can know this is a negative part. So K, then Fe. Given pentacyanido, cyanide and nitrosyl NO. For nitrosyl NO. between NO and cyanide, Cn comes first. In this is cyanide, as there are 5, so 5. This is a polyatomic ligand in parenthesis. Now, what is the charge? And charge of this iron is given 2, as this is 2. And nitrosyl, as given nitrosyl, this is a neutral ligand. As it is a neutral ligand, it has charge 0. So in this way, 2 plus 5 into -1, -5 plus 0 equal to -3. In this complex has, okay, so 2 is given 2, cyanide -5. And no, nitrosyl has 0. Nitrosyl has potassium, iron has given +2, it has +2. So 2 -5, 0. In this way it has -3. So this has charge -3 and this has charge +1. Just crisscross this number. In this way the formula found to be K3FeCl5 NO. Next come to question number 6. Amine chlorido bis ethylene diamine cobalt 3 ion. Ethylene diamine and chlorido. So this is an ionic part. In this is not in negative part. This is in positive part. This is no AT is there. So there is no AT. That means this is a positive part complex. Positive complex or cationic complex. As this is a cationic complex, then how to write the name? Amine chlorido. So amine is there for amine NH3. For amine NH3. For chlorido Cl minus. And for this En. Okay, and this present, that means these are 2 are present. So in this way, name of this compound is, so first cobalt, then chlorido and ethylene diamine. So chlorido is there and En is there. So between chlorido En, this will come first. So CO, then Cl, then between En and NH3, En comes first. So En2, then NH3. So CO, Cl, En2, NH3, and it has charge total given -1 and it has given 3. So 3 plus 3 -1 and these are neutral. In this way it has charge 2 plus. Okay, next come to tetraamine dichlorido cobalt ion. So this is also ion, one word. This is given amine, for amine NH3, for chlorido Cl. So in this way Cl should be written first. So first cobalt given dichlorido Cl2 tetraamine NH3 whole 4, and here the charge is also given. Here the charge is also given 3 ion. So as it has a +3 charge, that means oxidation number +3, 2Cl -2 is there. Sorry, -2, so +3 and -2 this cancels. It has charge +1. Okay. This is the next given pentaamine chlorido nickel 2 chloride. Pentaamine chlorido, come to 8. Pentaamine chlorido nickel 2 chloride. First given nickel, then pentaamine chlorido, so amine again NH3, and for chlorine Cl. So chlorido Cl minus, so in this is first Cl, so Cl pentaamine, then NH3 whole 5. Okay, so total coordination number is 6. This is the coordination sphere, and then chloride. So first find out what is its valency. So it has charge 2. As it has charge 2 and chlorine has charge -1, overall it has charge +1 and chloride has charge -1. In this way, no need to write any other number. This is just the formula of compound. So in this way, if name given, then we can write what is the formula, and if formula given, then we can write what is the name of the compound. Now next come to isomerism. So isomerism, actually here we are going to discuss about the structural isomerism. Isomerism not only given by organic compounds, these are also given by coordination compounds, because the coordinate bond is directional in character. So what is isomerism? You know, when the same molecular formula represents two or more compounds which have different arrangement of atoms or groups. When the same molecular formula represents two or more compounds which have different physical and chemical properties, then such compounds are called isomers, and this phenomenon is called isomerism. And for these compounds are isomers and isomerism. So for compounds which generally the compound generally exhibits two types of isomerism: structural isomerism and geometrical isomerism. And here we are going to discuss only about structural isomerism. In structural isomerism, these compounds have different structural arrangements. Same molecular formula, but they have different structural arrangements. Okay. So next come to structural isomerism. Structural isomerism in coordination compounds. Structural isomerism in coordination compounds. So the coordination compounds exhibit structural isomerism. So what are the different structural isomerisms? So the same molecular formula which represents different compounds which have different structural arrangement, that are known as the structural isomerism. So coordination compounds generally exhibit four types of structural isomerism. Generally it exhibits four types of structural isomerism. One, ionization isomerism. Ionization isomerism. Next, linkage hydrate isomerism. Hydrate isomerism. Linkage isomerism. Linkage isomerism. And another, coordination isomerism. Coordination isomerism. Okay, four types of isomerism. Let us discuss one by one. Ionization isomerism. When the same molecular formula represents two compounds which differ by giving different ions, or which have different ions are present around the ionization sphere, in ionization sphere, and where the ligands and ionization spheres some parts are different, then that are known as your ionization isomers, and this phenomenon is known as your isomerism. So when the same molecular formula represents two compounds, same molecular formula represents two compounds which give different ions in aqueous solution, simply which give different ions in aqueous solution, that are known as your ionization isomers, and this phenomenon is known as your ionization isomerism. Look at one example: CO, Br, NH345, SO4, and CO, SO4, NH345Br. Actually, this is the same molecular formula: one cobalt atom, one bromine atom, 5 ammonia molecule, 1 sulfate ion in both these cases. But here sulfate ion remains outside the coordination sphere, your bromide ion remains outside the coordination sphere. And this has color generally violet, and this has color in aqueous solution. This is violet color, and Generally this gives COBr whole 5 2 plus SO4 2 minus ion sulfate ion plus COBr whole 5 2 plus ion. It gives in aqueous solution COSO4 NH3 5 plus Br minus ion. In this way, these two give different ions. It gives white precipitate with barium chloride solution, and it do not give white precipitate with barium chloride solution. It gives yellow precipitate with silver nitrate solution. With silver nitrate solution, it gives yellow precipitate, and it gives white precipitate with barium chloride solution. So in this way, these two give different ions, although they have the same molecular formula. So this is known as your ionization isomers, and this phenomenon is known as your ionization isomerism. Okay. Next come to another, that is hybrid isomerism. So when the same molecular formula represents two or more compounds which are different number of water molecules inside and outside the coordination sphere, then that compounds are known as hybrid isomers, and this phenomenon is known as hybrid isomerism. Okay, so when the same molecular formula represents two compounds which are different number of water molecules inside and outside the coordination sphere. Look here, suppose you take the example of CrH2O whole 6 and Cl3. This is also one type of ionization isomer. CrH2O whole 6 Cl3. So in this coordination sphere there are 6 molecules, and here 3 chlorine atoms, 3 chloride ions. So this chloride ion can come here, and if water comes here, in this way we get CrH2O. 1 minute. So first chlorine CrClH2O whole 5 and Cl2 dot H2O and Cl2 H2O whole 4 Cl dot 2H2O and Cl3 H2O whole 3 and dot 3H2O. So these are some examples of hybrid isomers. In the same molecular formula, hexa aqua chromium 3 chloride and penta aqua chlorido chromium 3 chloride and monohydrate tetra aqua dichlorido chromium 2 chloride bihydrate. Similarly, tri aqua trichlorido chromium 3 and trihydrate chromium 3. So these are hybrid isomers of each other. Here the water molecules present inside and outside coordination sphere are different. Here water present as ligand, and here water present as in hydrate form. Okay. Now next come to linkage isomerism. Linkage isomerism. So when the same molecular formula represents two compounds which are differ by the point of attachment of different ligands, then that point of attachment of the same ligand at different sites, then that point of attachment of the same ligand at different sites, then that are known as your linkage isomerism. So linkage isomerism is generally given by the ligands where the ambidental ligands are present. Ambidental ligand means a ligand which have different donor sites, but at a time it can coordinate through only one bond. That is known as your ambidental ligand. Okay. For example, CO NH3 whole 5 O NO Cl2 and CO NH3 whole 5 NO2 Cl2. Both have the same formula, both give same ions here. Both are precipitated by aqueous solution of silver nitrate, but here this is attached to oxygen atom, this is nitrito O, and here this is attached by nitrogen atom, that is nitrito N. In this way, these two are linkage isomer of each other. So what is this? Is pentaamine. This is pentaamine, nitrito N, pentaamine nitrito N, cobalt 3 chloride, and this one what? Same pentaamine nitrito O. This one pentaamine nitrito O, cobalt 3 chloride. So whenever you write the names in isomerism, you have to write the names. Next, come to coordination isomerism. So coordination isomerism, these are the structural coordination isomers. These are the structural isomers which are formed by exchange of ligands. Here, so the same molecular formula represents different compounds of which are differ by the exchange of ligands, which are formed by the exchange of ligands, that are known as your coordination isomers. And coordination isomer is generally formed in that case where both the cation and anion both are complexes. That means where both cationic complex and anionic complex are present. In that case, coordination isomer are formed. Look at one example. Pt, platinum, NH3 whole 4 and CuCl4. So this is the positive part, this is the negative part. So tetraamine platinum 2, tetrachloridocuprate 2. Tetraamine platinum 2, tetrachloridocuprate 2. And suppose another Cu NH3 whole 4 and PtCl4, and this one is tetraamine copper 2, tetrachloridoplatinate 2. Tetraamine copper 2. So in this case, these ligands exchange their position. Here these amines are linked with platinum, and here these amines are linked with copper. Here chloride ions are linked with copper, and here chloride ions are linked with platinum. In this way, but the total molecular formula is same. In this way, these are known as coordination isomers. Okay. Next, come to another part. If the coordination compounds are formed, then to explain what are the bondings, what are the structures, the different scientists attempt, and they gave different postulates regarding this bonding and nature of a complex compound. So first time Werner in 1893, first he gave some postulates. First he formulated some postulates and explained what is the bonding of coordination compounds and the nature of compounds. Okay, so first he experienced, he has done experiment regarding these cobalt complexes. So different compounds are formed from cobalt chloride and ammonium hydroxide. By taking this cobalt chloride and ammonium hydroxide, he prepared a number of compounds, and from that he postulates some theories that are known as your Werner's theory. Okay, so next comes oneness theory. So this theory gives the preliminary idea about the bonding and the nature of coordination compounds. So according to him, the central metal atom of this coordination compound, the central metal atom with the coordination compound has two types of valencies, that is primary valency and secondary valency. Okay, so the primary valency, this is ionizable, and it refers to the oxidation number of the metal when the atom shows its normal salt. What the atom shows in its normal salt. And the secondary valency, this is non-ionizable, and it gives this is non-ionizable and it gives the geometry of this molecule. It gives the geometry of the molecule. Okay, geometry of the molecule, and it refers to the coordination number. So the primary valency, ionizable valency, refers to oxidation number. Secondary valency refers to the coordination number. So the secondary valency, this primary valency, it is non-directional. This is non-directional in character, and the secondary valency is directional in character. This is non-directional, this is directional in character. Every metal atom has its tendency to satisfy both its primary valency and secondary valency. So as they have two types of valency, they have also tendency to satisfy both its primary valency and secondary valencies. So these primary valencies are satisfied by negative ions. Primary valencies are satisfied by negative ions, whereas the negative valencies are satisfied the negative ions or neutral molecules that are ligands. Either negative ions or neutral molecules that are called ligands. So whenever they represent the structure at that time, so this is directional, this is non-directional, it decides the geometry of the molecule, it do not decide the geometry of the molecule. So the secondary valency is generally represented by some solid lines. When we write the structure of this compound, at that time we represent the secondary valencies by solid lines and this primary valencies by some dotted lines. Suppose we take the different compounds of cobalt amine complexes. The cobalt amine complexes. Suppose we consider about the cobalt amine complexes, then that can be represented by structural form like this. So COCl3 dot 6NH3. 6 ammonia molecules suppose there, that can be represented as every atom has a fixed number of secondary valency and every atom has a fixed number of secondary valency and primary valency may be variable. Okay, so primary valency is variable and secondary valency represents the geometry of the molecule. So as it has secondary valency here, it has secondary valency is 6. As the secondary valency is 6, so it has octahedral shape and these primary valencies are represented well. So these fluoride ions that are generally ionizable and these what are represented solid lines that are generally non-ionizable. In this way, the cobalt atom COCl3.6NH3 given this. So it gives. So nowadays these are represented as CONH3 whole 6 and Cl3. So these three chloride ions is ionizable. Similarly, suppose we consider the example of COCl3 dot high NH3, then then that can be represented as so it has a fixed number of coordination bond. So as it has a fixed number of secondary valency, so this geometry is fixed in this way. Here ammonia, 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 ammonia and ammonia, and here also no ammonia, here one chlorine atom. Here, so it has fixed number of secondary valency. To satisfy its secondary valency, one chlorine atom from this ionization sphere come to this coordination sphere. One chlorine atom from the ionization sphere come to the coordination sphere. In this way, chlorine here satisfies both primary valency and secondary valency, and this is represented nowadays CO, NH3, whole 5Cl and Cl2. So one chlorine atom comes here. The chlorine satisfies both its primary valency and secondary valency. Similarly, if we write the structure of COCl3 dot 4NH3, that can be represented as it has a fixed number. So first we have to fix its coordination number, its secondary valency. So you have to write the 6 ligand for if 4 ammonia are there, that are represented like this: ammonia, ammonia and ammonia, and these chlorine atoms, 2 chlorine atoms satisfy both its primary valency and secondary valency, and 1 chlorine atom like this. So CO, NH3 whole 4, Cl2 and Cl. Okay. Next, if there are similarly, if this compound can be represented as CO, NH3 like this, and chlorine and chlorine. Here these 3 chlorine atoms, CO, NH3 whole 3, Cl3. Here all the 3 chlorine atoms satisfies both its primary valency and secondary valencies. So in this way we can represent the different molecules. Okay, so it also explains about its chemical behavior. How many number of ions it can give, what is its conductance value. If it gives more number of ions, then it has conductance value higher. Then how much it can give precipitates. All this maximum chemical behavior of this complex can be the conductance behavior and maximum chemical behaviors can be explained by this Werner's theory. Okay, so for today up to this, next we will discuss some other parts of this chapter.